we were discussing the variation method, and specifically we were talking about the variation theorem, which says that script E, which is defined to be equal to for any acceptable state function phi. This quantity is guaranteed to be greater than or at the most equal to the ground state energy of the system. And therefore, if you have a system for which you want to calculate the ground state energy, all that you have to do is you have to guess an approximate wave function, put it in there into the expression, calculate it, the answer that you get will be greater than, that is guaranteed. It will be greater than, it may happen to be equal to, but that will happen only rarely. It will be greater than the actual ground state energy, and also it gives us a criterion to judge wave functions. If I have a wave function and if you have a wave function, the one that is better is the one that will give a lower value for script E. So, the question is now, how does one prove this? So, the way to prove this is quite simple actually. You know that there is a Schrodinger equation H psi is equal to E psi, and you also know that there are infinite number of eigenfunctions for the Hamiltonian operator having their own eigenvalues, their own energies. It is just that you are not able to find what they are, but we know that it is there. So, let me denote the eigenfunctions and the corresponding eigenvalues by the symbol psi 0, psi 1, psi 2, etc., and these have the energies E 0, E 1, E 2, etc. This we know, but unfortunately mathematically it is very difficult for me to find these functions and the corresponding energies, but as I said, we know that they are there, and I also know that these functions are actually orthogonal to one another. We have proved that if we have a Hermitian operator, then the eigenfunctions have to be orthogonal, and I can also take them to be normalized, each one of them, and further they form what is referred to as a complete set, which means that any arbitrary function which is an acceptable wave function can be expanded in terms of these functions. So, therefore, I can definitely say that phi may be written as C0 psi 0 plus C1 psi 1 plus C2 psi 2. This is definitely possible, even though I do not really know what the values of C0, C1, C2, C3, etc. are, but this is possible. And if that is possible, let me evaluate the numerator of this expression. What is the numerator? It is actually integral d2 phi star phi h phi, and that will be equal to, what is going to happen, you would have integral d2 C1 psi 1 plus C2 psi 2 plus etc. Oh well, I forgot to put C0. Let me modify this. C0 psi 0 plus C1 psi 1 plus C2 psi 2 plus etc. Then you will have H, and then you will have, of course I shouldn't forget the star, so there is a star on top of this. Then C0 psi 0 plus C1 psi 1 plus C2 psi 2 plus etc. Now, with this expression I can do two things. First of all, I can take this star operation inside, that means everything which is inside will be affected. each one of them is going to get a star, which means that I am just calculating the complex conjugate. That is the first thing. Not only that, I can take H inside and allow H to operate upon this sum. C0 is just a parameter or a constant expansion coefficient, actually strictly speaking. So this H can go and operate upon psi 0, then if it comes here, it will go operate upon psi 1, there it will operate upon psi 2 and so on. So therefore this is actually integral d2 C0 star psi 0 plus C1 star psi 1 plus C2 star psi 2. Well, I should also put star on this psi's. And when H goes inside, you are going to get C0 E0 psi 0 plus C1 E1 psi 1 plus etc. That is what is going to happen. Right? And now suppose I multiplied things out and did the integration. So what is going to happen? Let me demonstrate to you this term I can multiply with that. What will be the result? The result will be C0 star. From here there will be a C0 from there, there will be an E0 from here, and I will have integral psi 0 star psi 0 d2. That will be the first term, correct? And I can simplify this because I know that psi 0 is a normalized function. So that integral that is occurring there, this must be equal to unity. Then the next term will be actually, I could write it as integral d2, well, C0 star, let me put first, then I am going to take this and combine it with that. C0 star C1 E1, these are all position independent, so I can take it out of the integral sign, and what will I have? Psi 0 star psi 1 d2. There are other terms, but you can easily see what is going to happen. This term is 1 while that term is 0. And similarly, if we had taken this psi 0 star multiplied with any other psi, answer is going to be 0. So therefore, from this multiplying all those terms there, you are going to get only one term. And what is that one term? Maybe I can just remove these things that I have written and just write that one term alone. This is that one term. Then similar thing is going to happen with C1 star psi 1 star. So it again multiplying all these terms, you see almost every term is 0 except the one that will involve psi 1 star psi 1. And what will that term be? That is going to be equal to C1 star C1 E1. And then you will have C2 star, it is very obvious, C2 star C2 E2 plus etc. This is what is going to happen. And now we look at the numerator. What is the numerator? Integral d2 phi star phi. It's going to be integral d2 C0 psi 0 plus C1 psi 1 plus etc. with a star multiplied by C0 psi 0 plus C1 psi 1 plus etc. This is what is going to happen, but in fact this term is even simpler than the previous one, because see all that is happening is that there is no H in between. The previous term had an H in between, and that H gave you this E0, E1, E2 etc. But now you see the H is not there, so you are not going to have E0, E1, E2 etc. But other than that things are the same. So therefore what will happen? I can just take these result, remove E0, E1, E2, E3 etc. That is the answer. So therefore this is going to be C0 star C0 plus C1 star C1 plus C2 star C2 plus etc. And therefore script E What is the expression for script E? We have evaluated both the numerator and the denominator. The numerator is this is what it is. So, what I want to do is, you see, I am going to subtract an E0 from here. So, let me remove this E and say that I will have a script E minus E0. All that I need to do is I will add another E0 here. I mean, I'm sorry, not add, but subtract an E0 from the right hand side. That is all that I need to do. And now you see this also, this E0 also can be incorporated into the numerator, right. So, what you have to do is you will have C0 star C0 E0 plus E1 star C1 E1 plus C2 star C2 E2 plus etc. minus E0 C0 star C0 plus C1 star C1 plus etc. divided by So, actually it is very clear that this term and that term will cancel each other. One term actually cancels and you are left with the remaining terms, and the remaining terms I am going to write in this fashion. I would have, well, if you think of C1 star C1, you are taking the number C1, multiplying it by its own complex conjugate, that is actually equivalent to calculating the magnitude of C1 and squaring it. So, this is nothing but magnitude of C1 square, and what are you going to have? You are going to have E1 minus E0, because here there is a term involving C1 star C1, there also there is a term involving C1 star C1, and I can combine both the terms. And the next term is going to be C2 magnitude square E2 minus E0 plus C3 magnitude square E3 minus E0 plus etc. divided by magnitude of C1 square, magnitude of C2 square plus etc. This is what happens. Fine. Now, if you look at this, you see these numbers C1 magnitude of C1 square, magnitude of C2 square, they are all positive, absolutely no doubt, magnitude square. What about E1 minus E0? E0 is the energy of the lowest possible state, E1 is the energy of the next possible state. So, E1 minus E0 has to be positive, there is no other way. E2 minus E0 again positive, E3 minus E0. So, therefore, you realize that all the terms on this side are positive. That is all that I need, and therefore, I can say that this has to be greater than or equal to 0, because everything on the right hand side is positive. In the case where it so suppose it so happened that C1, C2, C3 etc. are all 0, C1, C2, C3 etc. are all 0, then it is theoretically possible that it may be equal to 0. But then what would happen? The C1, C2, C3 etc. are all equal to 0 actually. So, therefore, phi will be equal to psi 0. So, you have somehow managed to choose the actual ground state wave function. As I said, that is not very likely, and therefore, this equal sign will be valid only rarely. It is always the case that it is greater than 0, but theoretically this is possible, and therefore we have to put greater than or equal to sign. So now you see, I want to develop a practical procedure for calculating energy subsystems and actually use it in real problems that are of chemical interest. So how am I going to do that? Let me tell you how it may be done, and then I shall demonstrate it by applying it to some problems that are of great interest to the chemists. See, for the case of a particle in a one dimensional box extending from 0 to a, we said that an appropriate wave function would have to have its value there 0 and its value on the other side also equal to 0. So we decided to try phi equal to x into a minus x, correct. This is a problem for which we know the lowest possible state's energy, which is E1, and that is equal to pi square h cross square divided by 2 ma square. This is the correct answer, exact answer, and we evaluated script E, and what happened was actually you got 10 h cross square divided by 2 ma square. This is what you got. So instead of pi square, you had a number 10 sitting there, and pi square is about 9.84. So I said the error is about 1.6%. But suppose you are not happy with that. Suppose I want to improve this function. I want to do a better calculation for some reason. I am not happy with this 1.6% error. I want to make it a better calculation. So how can I do that? To do that, you see, I will have to somehow think of a better wave function, correct. That is what I have to do. How can I think of a better wave function? Well, any function that I would choose would have to have a vanishing value at this point as well as at that point. So what I will do is, I will think of another possible function, which I will write as x square into x minus a the whole square. This also will satisfy the condition that it will vanish at the origin, it will also vanish at a. Now, so you can actually try calculating with this function alone, you will find that it does not improve the energy, it does not give you a better energy. Okay. I mean, I am not going to do the exercise, but it is possible to do the calculation. So if that is the case, what you can do is, you can say, okay, what I will do is, I will take a combination of this and that with some coefficient here, okay, and that coefficient is, it's my choice, I can choose any value for the coefficient. I will definitely have an acceptable wave function. Now, for dimensional reasons, what I will do is, I will just take that coefficient to be alpha by a square. This is only for dimensional reasons. I mean, if you are puzzled by this, you say, you think of the dimension of this is having the dimension of length square, and I want this other function also, which this is my other function, this whole thing also to have the dimensions of length square. So that alpha will be a dimensionless parameter. It is not really necessary to include this a square here. You can say you will not include that, then what will happen is that alpha would have the dimensions of length square. So I do not want that, I want it to be dimensionless, so I include this. Now I know that if I did a calculation with alpha equal to 0, what will happen? I am going to get this as the answer. If I did a calculation with alpha equal to 0, this is the answer, which means that script E divided by h cross square 2 ma square will actually be equal to 10 when alpha is equal to 0, correct. Now what I am going to do is I am going to use other values of alpha, right. So what will happen, something is going to happen to the value of script E. So script E will now depend upon the value of alpha. So you can think of script E, it is now a function of alpha. What you can do is these days you say this kind of calculations are extremely easy, particularly if you use this software Mathematica, you can do it in a second. Otherwise you will have to do the calculations anyway, I mean they are not very difficult calculations, but you can do it. And what you do is I am not going to give you any expression, but what is interesting is to make a plot of E alpha against alpha, okay. And in the same plot, well I will not plot E alpha, but I will plot h cross, this divided by h cross square divided by 2m a square, this is the number that I am going to plot. And I know that when alpha is equal to 0, it has the value 10. And I will also plot the actual ground state energy. How much is the actual ground state energy? The expression is written there. So you can say, okay, in the same figure I am also going to represent E1 divided by the same object, h cross square divided by 2m a square, which I know is pi square, right. So in the same figure I can represent that. Maybe what will happen is that does not depend upon alpha. So if you plotted it as a function of alpha, all that you are going to get is a horizontal line. This is that number. And now if you plotted this object as a function of alpha, what are you going to get? You will get a curve, but the variation theorem ensures that this curve that I get will always be above E0, sorry not E0, but the ground state energy, which in this case is E1. So therefore actually if you did this calculation, you will find that the curve that you get gets very close to E0, sorry again I say E0 because it is the ground state energy, but in this particular case it is E1. So it does this and then it goes and becomes large, something like that. I mean and in fact the energy that you get is very close to the actual ground state energy. It happens, I do not remember now, but about 1 alpha is approximately 1 or some such number. That is not very important, but the important thing is that as you change the value of alpha, the curve gives you a minimum and then increases. And what is the best possible value for alpha? The best possible value for alpha will be the one that minimizes script E, right. It has to E, this E is a function of alpha. All that I should do is I should find that value of alpha which minimizes this. In fact, if you know what this function is, this is a very simple exercise in calculus. What is the exercise? You will say, okay, the derivative of script E with respect to alpha should be equal to 0. You find that and that will give me the best possible value for this parameter alpha. Now this gives me an idea. What is the idea? You see, if I have a wave function, a trial wave function which contains some parameters like alpha here, or in a different problem it may be a different parameter, then what will happen? My script E is going to depend upon that parameter, and what will be the best possible value for that parameter? You have to find that value in such a fashion that script E has the least possible value. It is script E has to be a minimum, right. That will be the best possible value that you can choose for alpha, and therefore we have a very rigorous way of making our wave function better and better if you want. I mean what you should do is you should write wave functions which have maybe several parameters, and then find the optimum values of these parameters by minimizing the expectation value of energy. And as I told you, this is the procedure that is adopted in all the molecular orbit, most of the molecular orbital calculations that are being performed. Okay. So, let us now think of a real chemical example, which will be the case of helium atom. So, what is the helium atom? Well, I have at the nucleus, I have the 2 electrons 1 and 2, and the electron 1 would be at a distance which I denote as R1, electron 2 would be at a distance which I denote as R2. Electron 1 has the coordinates x1, y1, z1. This has the coordinates x2, y2, z2. Strictly speaking, I should think of the motion of the system as a whole, that is translational motion. But as I have demonstrated to you in the case of the hydrogen atom, we can get rid of translational motion, and then there will be some effective masses coming into the description of the problem. But from now on, we are not going to use any, when I say effective, what I mean is actually this reduced mass that was there in the case of the hydrogen atom. So, from now on, this is a minor correction. So, from now on, I am not going to use the reduced masses or anything, I am just going to use the masses of these electrons. So, let me just put m here and m, and I will assume that the nucleus may be thought of as fixed at the origin. Okay. So, we are not actually worried about the translational motion of the system, because you see in chemistry most of the time we are interested in the electronic structure. Of course, there are any number of problems in which you have to worry about translational motion, but that is not what we do now. So, what will be the Hamiltonian for the system? Well, the way we are operating, nucleus is taken to be fixed at the origin, and therefore, we are not worried about the nuclear kinetic energy, we are worried about the kinetic energy of electron 1, kinetic energy of electron 2. So, what will happen? Minus h cross square divided by 2m del 1 square minus h cross square by 2m del 2 square. These are kinetic energies of the 2 electrons. Then I would have minus 2 e square divided by 4 pi epsilon 0 r1 minus 2 e square divided by 4 pi epsilon 0 r2, and there is repulsion between the two, e square by 4 pi epsilon 0 r12. Right, you have a 2 here, you have a 2 there. The reason is that I am thinking of a helium nucleus. I can immediately generalize this and say, let us not worry about helium atom, but let us think of a general situation where the nuclear charge may be taken to be capital Z. So, that this treatment that I am going to give you may be applicable for all values of nuclear charges. The only thing is that there should only be 2 electrons, right. If you are thinking of helium atom, the value of capital Z will be equal to 2, but if you are thinking of lithium ion Li plus, the same Hamiltonian would be valid, okay, but the value of Z will then be equal to 3. Okay. So, we can have a general treatment, you can say even it will be applicable to H minus if the species existed, because H minus would have a capital Z equal to 1, right. So, let me keep this general and say that, okay, this charge, instead of this 2, you are going to have a capital Z. Do not confuse it with the Z coordinate. I am using a capital Z, and here also a capital Z. And so, what is the problem now? I have H psi equal to E psi. This is the equation that I want to solve, but in this case what is going to happen is that psi is going to depend upon the position coordinates of the two particles. So, how many position coordinates? Actually 6 of them, x1 y1 z1 x2 y2 z2, but it is tedious to write x1 y1 z1 x2 y2 z2. So, therefore, what I will do is I will say position vector of the electron 1. Now, here you see I have introduced r1, this r1 is actually the distance, but this object is the position vector. So, this is a vector, and in fact the magnitude of this vector will be equal to that r1. So, if you put a line on top of it, that is the position vector. If you do not put a line on top of it, then that is just the distance of the electron from the nucleus, right. So, this will actually, I mean, if you want to be very precise, you can say r1 will be x1 i plus y1 j plus z1 into k, and similarly you will have another expression for position vector of the electron 2. So, therefore, I mean, this is very convenient because we do not have to do write x1 y1 z1 x2 y2 z2 and so on. And then this psi on the other side will also be dependent upon r1 r2. So, that is how things are. Now, this equation, if you look at this, very messy because it involves 6 variables, partial differential equation involving 6 variables. As I repeatedly say, even an ordinary differential equation can be extremely difficult to solve, and so a partial differential equation involving 6 variables almost impossible to solve, and so we have to think of some approximate procedure. Okay. So, how will we go about doing it? Well, before I go about doing it, actually I want to understand what is the problem, where is the problem, and why is it that I cannot solve this, right. I mean, there should be a physical reason. You see, any tough problem, there will be a physical reason why it is not possible to solve it. Now, for a moment imagine that these electrons, you see, they do not repel each other. Suppose, I mean, that is not the actual physical situation, but imagine, I am going to imagine that they do not repel each other. If they do not repel each other, what will happen? This term is not going to be there, and then what will happen? You will have a sum of things that depend only upon the coordinates of electron 1. Notice this depends only upon the coordinates of electron 1, while this part depends only upon the coordinates of electron 2. So, therefore, you have kinetic energy of electron 1 is interacting with the nucleus, then you have kinetic energy of electron 2 is interacting with the nucleus. The two electrons do not feel the presence of one another, right. So, what will happen? Each electron will move independently of the other electron, right. See, the two electrons are not repelling each other. So, therefore, each electron moves independently of the other electron. Each electron feels only the nucleus, and so the motion of the electron will be similar to that in the case of the hydrogen atom, right. And you can actually exactly solve for motion of each electron. So, each electron, what will happen? It will be governed by an equation which I may write as minus h cross square by 2m del 1 square minus z e square divided by 4 pi epsilon 0 r1. This will be the kinetic energy of electron 1, potential energy of electron 1 due to its interaction with the nucleus, and you will say, okay, there is a wave function which will depend upon the coordinates of that electron alone, right. And I actually have to be a little bit careful because I have introduced one psi here, another psi there, and they are not the same. This psi is a function of 6 variables, while this psi is a function of 3 variables, and so because I have used the same symbol, there is a possibility that you may get confused, and therefore, what I am going to do is I am going to denote maybe this by capital psi. If I added this, I mean that is the minimum change that I can make. I say this is capital psi and that also is capital psi, but this one the way it is written, I hope you can recognize this as small psi, not capital. And what is going to happen is, you see, this will have its own energy, which is going to be E1 psi R1. And a similar equation should be valid for electron 2, and there also I will have a function, right. There also I am going to have a function, correct, which will be the wave function for electron 2. And what are the solutions of this equation? Same as in the case of the hydrogen atom, but for the fact that the nuclear charge is not equal to 1, but it is equal to Z. So, therefore, I should tell you what happens. I mean the process of solution can be carried out easily, we have already done it. So, all that will happen is that the allowed energy levels, this E1 for example will be given by I do need the expression. So, I can't remember it, I will just copy it from my notes. You are going to get minus m e to the power of 4 divided by 32 pi square h cross square epsilon 0 square into 1 by n square. This was just the expression for the hydrogen atom, except for the fact that I have not used the reduced mass here, I have just put the electronic mass, but reduced mass and the electronic mass are only slightly different. So, as I said, we are not going to worry about that difference. So, this is the expression, but this definitely is not correct, because you see the nuclear charge is not there in the equation. So, what actually happens is extremely simple, you will have Z square sitting there. Okay. And then you will have the wave function also. The wave function, what will happen is that I mean I am not going to worry about all the possible wave functions, just as in the case of the hydrogen atom, we have all the possible wave functions. Specifically I am interested in the ground state of helium atom. So, therefore, what will happen is that I will have the lowest possible state, which will be psi 1s, okay. And psi 1s, I know it will depend only upon R1, it depends only upon the distance of the electron from the nucleus, I know that. And what was the expression that we had? It was actually 1 by square root of pi I think we wrote it in this fashion, A0 to the right, this is, you can check this, then you will have e to the power of minus r by A0. This was, well, this was the solution for the case of the hydrogen atom for the 1s orbital, right, this is correct. But of course, this is not valid for this particular problem, because the nuclear charge is not unity. This would be valid if the nuclear charge was 1 unit. So, what actually happens is you will have capital Z to the power of 3 by 2 sitting here and a capital Z sitting there, and not only that, this is the distance of electron 1, r is the distance of electron 1 from the nucleus, and therefore, you will have to put r1 here. So, that will be psi 1s. And what will be the corresponding energy? All that you need to do is you have to put, if you are thinking of this particular state, you have to put n equal to 1, because you are thinking of the lowest possible state. Again, strictly speaking, I should say that there is going to be an n1, this is the quantum number associated with electron 1, right. It is not just n would be the case if you had only 1 electron, but now here I have 2 electrons. So, therefore, I have to distinguish between them, and therefore, it is better that I put a subscript there and write it as n1. Now, you will definitely agree with me that this is all very messy, because there are so many constants, right. You have M, you have E, you have H cross, what else do you have? You have epsilon 0 and so on. And usually in quantum chemistry, one therefore changes to another system of units. This is written in SI units, so to say. I mean, you will have to put in the SI values for M, E and so on. So, what we will do is, we will think of changing over to another system of units which are referred to as atomic units. See, in SI, for example, you know that meter is the unit of length, kilogram is the unit of mass, right. Now, these things are not very good for describing things happening at the atomic level, because atom is so small, right. So, it is better that we do not use these SI units, but we use something else. And what would that something be? The answer is that, you see, in the Bohr theory, you know that there is this first Bohr orbit, it has a radius a0, right. It has a radius a0, and that is an appropriate unit for length, because the size of the atom is roughly a0. So, therefore, I will take a0 as my unit of length. I will take electronic mass as my unit of mass, correct. And if you do similar things, I mean, similarly you can define a unit of time. The nice thing is that if you did that in this system of units, what happens is that a0 is 1. Interestingly, H cross will have a value unity. Everything actually simplifies. 4 pi epsilon 0 will have a value unity, and as I told you, mass of the electron again has a value unity. So, very nice system of units, because if you look at this expression, you have H cross here, H cross is 1, M is the mass of the electron, that is 1, E again has the value unity. So, E becomes unity, okay. So, E has the value unity, 4 pi epsilon 0 which is occurring there, that also has the value unity. So, therefore, this equation actually becomes minus half del 1 square minus Z divided by R1. But now you should remember that R1 is measured in atomic units, right. If you say R1 has a value equal to 1, that actually means that the electron is at a distance a0 from the nucleus, that is the meaning, right. And this operating upon psi R1 will be equal to E1. What will be the expression for E1? That also we can simplify, because M is 1, E is 1, in here 4 pi epsilon 0 is 1, 4 pi epsilon 0 is 1, H cross is 1. So, if you did all that, what will happen is that this E1 will get transformed. You can easily verify this, it will become simply minus 1 by 2 n square or n1 square. So, again in this system of units, you see energy has a very simple appearance. All these constants we can get rid of, and you will say, okay, it is actually minus 1 by 2 n1 square is the expression for the allowed energy levels of the system, and this is in atomic units, right. Now, you would already know that the ionization potential of, well, you should not forget this Z, right, because I mean the Z is, you are not saying it is 1, because it is not the hydrogen atom, it is general. So, then this is energy, remember this is energy, and this is energy expressed in atomic units of energy, okay. And what is the atomic unit of energy? Well, you can find that by using calculations, but we will not do that. We will say that 1 atomic unit of energy is equal to 27.2 electron volts. This is all that we need, okay. Now, if you want to just check this, what you can do is you think of the ground state of hydrogen atom, for hydrogen atom Z is 1, ground state means n is, the quantum number n is 1. So, therefore, what will happen, you will get a simple answer minus half. So, this is in atomic units, but you know that the energy of an electron in the hydrogen atom expressed in terms of electron volts is minus 13.6. So, this is in atomic units. In our other calculations, you would know that this is actually minus 13.6, which immediately tells you that 1 atomic unit of energy is nothing but 27.2 electron volts. So, that is convenient. I mean, this is very nice, because you see, if you look at this Hamiltonian, what is going to happen, you will see that it simplifies enormously. Even the Hamiltonian for the helium atom, this will be just half. This will be just half. This will be Z by R1, that will be Z by R1, and what will happen to this will be just 1 by R12. So, therefore, the Hamiltonian's appearance is very nice and simplified, and therefore, atomic units are very convenient. You do not have, even writing is very easy. And what will happen to the wave function? Well, wave function also gets very simplified, because this A0 is now 1. In atomic units, A0 is 1, so you can remove that. You can remove this A0, and therefore, the wave function will become that is all. So, from this point onwards, we decide we do not want to use the usual system of units, but we will stick to atomic units, and because it is extremely convenient. And so, let us do that here with this Hamiltonian. So, here is the Hamiltonian for the helium like atom, and let us see what happens to this atom when we write it in atomic units. Remember, in atomic units, H cross will be equal to 1, mass of the electron will be 1. So, H cross by this H cross will become unity, that will become unity, 4 pi epsilon 0 is unity. So, E is unity. So, let me just modify the Hamiltonian on the board itself. M is 1, so that goes H cross square is 1. So, you will get that. Here again the same thing happens. You get 1 here, M is 1, Z square, the electronic charge is taken to be unity. So, this is 1, 4 pi epsilon 0 is unity, 4 pi epsilon 0 here, 4 pi epsilon 0 there, they are all unity, E square here is unity, E square there, where there will become unity, and you can see that now the Hamiltonian actually looks very nice. And even here, I mean, it gets modified. In fact, you are going to get minus E1 psi of R1, and E1 has a simple expression. E1 is actually given by this. So, this is for the first electron. What will happen to the second electron? It will obey exactly the same kind of equation, and if I am interested in the ground state of the hydrogen, sorry, not hydrogen but helium atom, what will happen? If there is no electron repulsion, the wave function for the first electron will be given by this 1s atomic orbital, which unfortunately I have rubbed off. So, therefore, let me write it once more. Psi 1s R1 is equal to how much? Z cube root pi e to the power of minus Z R1. This is the wave function. So, if you are thinking of the first electron, it will be sitting in the 1s atomic orbital. This will be the wave function. If you think of the second electron, If there is no electron electron repulsion, you can say that it is going to sit in the same orbital and its wave function will be given by precisely the same expression. So, you are going to have psi 1 as R2, because I am thinking of the second electron, that is going to be Z to the power of 3 by 2 divided by root pi e to the power of minus Z R2. So, electron 1 has this wave function, electron 2 has that wave function, and therefore, the entire system, you see the two are moving independently of each other. And so, what will happen? The total wave function will turn out to be simply a product. I mean, in a sense you can say, okay, the system is separable. Remember, we had method of separation of variables. So, if I want it to be rigorous, what I can do is I can neglect this electron electron repulsion, then use the method of separation of variables to get the solution. And in the method of separation of variables, what will you do? You will say that the total wave function is a product of two parts, one depending only upon electron 1, other depending only upon electron 2, and then you are going to get all these equations which may be solved. Okay, we will continue in the next lecture. Thank you for listening.